This is lecture 4 for chapter 5 for Calculus 3, and in this lecture I'll discuss two important conservative vector fields. There's homework associated with these vector fields. Okay, let's look first at the gravitational field. And I want to just discuss a little bit about its form and how why it's written the way it is. So what is a gravitational field? It states that there's a field between two masses, okay, and the field between the two masses is on a direct line between them and varies as the inverse square of the distance between them. And this is how it's typically written. So this will be your vector field. Remember, it has three components because it's a vector field. The little m, the big M, and G, don't worry about those. There'll be different constants when we do. They're just constants, and you can even divide them out. But look at the form of it. You have an x here, and in the denominator you have something to the 3/2 power, and it's the same for all three of them. Okay, I just want to show you how this is we kind of get the form of these equations. I remember looking at these initially when I first saw them and saying, square the distance, what's the 3/2 power doing there? And so anyway, let's derive that a little bit here. Let's write the force in terms of a vector, and the vector is going to be x, y, z, and the reason for that is we're going to put one of the masses at the origin, and then r will be the vector from the origin. Let me try to draw that for you a little bit. So we have some kind of coordinate system here, and here's the origin. We'll put one of the masses here. And up here we'll put the other mass. So we're talking about a straight line distance between them. So that was hardly a straight line, but you can imagine it's a straight line. That's a straight line between them, and x, y, z is a location of the other mass. So that's why we write r like that. What is its magnitude? Obviously, magnitude is just r dot r, square root, so that's x squared plus y squared plus z squared to the 1/2 power. Now I'm going to rewrite this equation in terms of that r. So again, I have my constant minus m, big M, and G, gravitational constant. And now the xi, the yj, and the zk, those are up here, really make up the r vector. So I'll write the r vector here. Looking in the denominator is the magnitude of r cubed. All right. Now break this out. This could stay as a magnitude of r squared, and I'll put the vector r divided by its magnitude right here. Now remember, the whole time we were doing the t, b, and n vectors, we kept working with a unit vector in a direction. We separated vectors out into their, well, any vector, let's just say vector v, into its magnitude, and to a unit vector in its direction, so that would be magnitude v times v over the magnitude of v. And this was that unit vector. So we see that this is the unit vector in that direction. Okay, and now you see the magnitude of r, of course, is the distance between the origin and this point x, y, z. So now you see that the force, this gravitational force, is varying as 1 over the distance between them squared, between the two masses squared. Some of you study physics a lot. This is, you know all this, but some people haven't studied physics as much. Now let's look at the electric force, between two charges, little q, big Q. We'll put big Q at the origin. We'll let little q sit at point x, y, z, just like we did before. And you see we get exactly the same equations here. A little bit of sign difference. Now notice that I'm putting a k up here, and I'm just going to criticize someone who wrote the textbook, one of the textbooks, Stewart. He uses epsilon for k. That's a bad idea, I think, because what does k turn out to be? 1 over 4 pi epsilon naught, which is the standard notation for the permittivity of free space. So I wouldn't use this permittivity symbol, typical physics permittivity symbol, for something which just really needs a constant k. Okay, so let that k sit there, and I just wanted to make that point. When you look at Stewart, you might want to cross that off and replace it with a k. Okay, so here we have just the same as before. We'll put those constants out in front. We have xi plus yj plus zk, x squared, y squared, z squared to the 3/2 power. Obviously, this is the same equation that we had before. Now we get some other important fields. If we divide out the little mass m, which is maybe arbitrary, or the q, the little q, the ones that's sitting off the origin, we'll divide those out, and what do we get? We get force per unit mass or force per unit charge, which is handy to have, right? Okay, so for the gravitational field, force is really mass times acceleration, right? Okay, so we divide this gravitational force by m, we get an acceleration due to gravity. Notice this is a vector. We tend to forget about this because we just look at the mass at the center of the earth, but it is a vector. Okay, so here we've got this vector minus mg. Remember, we divided out the little mass, and we have the same form, a unit vector divided by the magnitude of r squared. When we do the same thing for the electric field, we get something that also has physical significance, or electric force, I'm sorry. We end up with the electric field. And you can see it again, it's exactly the same equation as before, with a few constants changed. Both of these fields are conservative. That means they're the gradient of some scalar potential function. Okay, that's what conservative means. Let me get this other pen. The gradient of a scalar potential function. For gravity, the scalar potential function is called the gravitational potential, and here's what it looks like. In the homework, I give you the potential, which is voltage potential for the electric field, and you have to show that it's true by taking derivatives. But here, this is just an example here. Now, I want to show you this picture because it's important. Here is the gravitational potential is the scalar field. Right here, you can consider that to be the location of the big mass m, and obviously the distance from the big mass m to itself is 0. At this point, you have this pole, singularity, I'm going to call it, okay, right here. And then you see how this spreads out from it. Oh, I don't know if you can see this very well, but the reason I'm pointing this out is because this is what we did for gradient fields before, and now it has real application. Remember, you have the gradient of f, and if the direction of the gradient of f was the steepest gradient of steepest ascent, and the opposite to it, 180 degrees off, was steepest descent, perpendicular to it were the contour lines. What you're seeing here, the circles are the contour lines. Those are lines of equal potential. Okay, those are circles, and I think on your notes you can be able to see that those are circles better than you can up here on this slide. Okay, now perpendicular to those circles are these lines that are extending out from the pole. Those are the lines of the field, but remember the field was equal to the gradient of f, so you see they're going to point in the direction of f, which is the direction of steepest ascent. Perpendicular to f are those contour lines. So hopefully that will bring some of the previous chapter and this chapter together. Now I'm going to go through sort of in the opposite direction of deriving these equations for the electric field. It'll be similar for the gravitational field, of course, and in this case we'll encounter, and I will repeat some of the things that I already talked about, but it's okay to see it from a different direction. So we're talking about electric force, and say it is known from experimentation that the following hold. The magnitude of the force between two charges, we'll say little q and big Q, varies inversely with the square of the distance between them, you know that, and its magnitude is directly proportional to the product of the two charges, not the sum, not the difference, the product, and that the direction of force is along a line, a straight line between these charges, and this is what is known from experimentation. So we can take these and we can write the start of some equation. Actually, we write the whole equation, but all we're talking about now is the magnitude of the force and how it varies. So this is the magnitude of the force, so I'll write it with, I think in the text sometimes they do this, but they just write it as F without being in bold, and that can be confusing. So I'm going to go ahead and put the absolute value signs on, showing I mean the magnitude of F. I should have actually put doubles because it's a vector, but okay. So the magnitude of the force is proportional to the product of the two charges, little q and big Q, and it's proportional, so of course we have to have a constant proportionality, which is a k. It varies inversely as the square of the distance between them, which I'm writing as little r squared, which I probably should have written as the magnitude of r, but I'll do that later. Okay? So this just is an equation that summarizes experimental results. But what we're after is the force vector. We want the vector equation because we want to see those vectors in space. So we have to put a coordinate system. We have to work these out into vectors. Again, we're putting Q at the origin, the big Q at the origin, and the little q, which is like your arbitrary charge at some arbitrary point x, y, z. So now draw the line from the origin out to the two charges, and we get, just as before, xi plus yj plus zk. This is the line going from the origin, where big Q is sitting, to xyz, where little q is sitting. And what's the distance, and what are the unit vectors? We can just put that in here. The unit vector, of course, will be r over its magnitude, and the magnitude of r is the distance, and we want that squared. So we can either write it as r over magnitude of r, or if we pull this magnitude of r and combine it with this magnitude of r squared, we get magnitude of r cubed. Which again, maybe some people, no problem for them, but when I first saw this, I thought, why is there a cube? And now you know. Now it doesn't take much to go from this idea out to the xyz components, so we just put the components in and we get this equation, which we pointed out at first was in terms of xyz and in Cartesian coordinates. Here is the expression for the electric force between two charges. The field, and excuse me if I said field when I was talking about F, I really meant force, but the field is just F divided by little q, by the arbitrary charge. And we can do the same thing. We can write the electric field in terms of the xyz components, or we can write it in terms of r. And now we need to show, I said that the electric field is conservative vector field. I don't want to see this. I'm going to have to apply the component derivative test for conservative fields and see what happens. Here is a component test, again for reference, and all these three have to hold. M is the I component of E, N is the J component of E, and P is the K component of E. Okay, so when I take these derivatives, I get something like this. You get a chance to do this in homework, and you will see that, let me clear the screen for a minute. Okay, you'll see that the derivative of P with respect to Y does indeed equal the derivative of N with respect to Z. P with respect to X equals the derivative of M with respect to Z, and the partial of M with respect to Y equals the partial of N with respect to X. There's your component test. It passes all three. Now for your homework, I'd like you to work this out for yourself and make sure that it's correct. From the component test, we know that the electric field is a conservative field, and therefore it's a gradient of some scalar field called the potential, but we don't know what the potential is. So here, as in the homework, I give you the potential. It's actually voltage, and here's its form, minus kq over r. That's the voltage. And it's a scalar function. It assigns a value of voltage to every point in space. A scalar value, not a vector. The electric field is a vector, the voltage is a scalar. Okay, so when you start working this out, you can, well, of course, just put it into Cartesian coordinates and then take some derivatives to see if it's true. So although we've established that the electric field is conservative, it has to be the gradient of some scalar field. On the previous slide and in the homework, I give you the scalar field, and you have to show that its gradient equals the electric field expression that was derived earlier. In other words, we're trying to show this. Okay, modulo some signs, but we'll just leave it like that. So we're taking the gradient of F, remember that's del applied, a gradient of V. We're taking del applied to V, and the expression we have from V from the previous page. We take those partial derivatives, And we're going to get a vector out of it, and that's good because E is a vector. Alright, write out in terms of the ijk components, and establish that this is indeed the electric field. Now, if you recall from the previous lecture, number 3, conservative fields have some properties associated with them. One is that a line integral of a conservative field depends only on the difference of the potential at the endpoints. So if we're integrating the electric field along some line, along some path, the value of this depends only on the voltage at the end of the path minus the voltage at the beginning of the path. It doesn't matter what path I took, and I'll show that in a diagram in a minute. It also says, and of course would follow just from the fact that A and A are the same, but if you take the line integral of the electric field, a conservative field, along a closed path, it's going to be 0. Also, an electric field is irrotational, meaning that del cross E is 0 by the del identity established in lecture 2. Here's some graphs of electric fields and voltages just to show you what we're talking about here. Okay, in this case we have a point charge sitting right at the origin, whoops, and that would be your big Q sitting right here at the center, and out from it are lines of electric field. And remember, this is electric field and it's a gradient of a potential. So the gradient of a potential field is a vector. The direction that it's pointing, okay, that's a direction of greatest change. All right, and perpendicular to it, you see these circles. Okay, those circles are the contour lines. Okay, they are perpendicular to E. They're also, which means they're perpendicular to the gradient of V. So they are lines of equipotential, similar to what I was trying to show for the gravitational field. This is a more complicated one over here where you have 2 charges, just to show you that the pattern gets more complicated with more charges. It's just for one. And now in this case we're looking at the field going from this 4-volt kind of assembly of charges making 4 volts down to 0 volts here. Okay, the field, these are your lines of equal potential lines. So everything on this dash line is 3 volts. Everything on this dash line is 2 volts. Everything on this dash line is 1 volt. What does the electric field look like? It's going to be perpendicular to the lines. So we're kind of looking at a different idea than we did up in this one. Okay, so here we have sketched out here these lines of equal potential, and what is shown here is that the electric field is at right angles to those lines, to those contour lines of equal potential, because the contours are perpendicular to the gradient. Also, the idea of the line integral of V dot ds means that if I'm integrating this electric field along any path from here to here, this is kind of a long path, this one is a short path, it doesn't matter whether it's longer or shorter, it only depends on the endpoints of the voltage. The difference in the voltage of the endpoints would be 0 minus 4. Okay, in this case, going from here to here, or even going back, you'd have a sign change. I use that in homework, and it's also on an exam. Let me clear the page for a minute. Okay, on the exam, I have a different kind of situation. So let's say you have, here's a blow up of this case. Okay, and let's say this is 10 volts and this is 5 volts. Now, change color here so that you can see what's going on. If you start here, some charge, and you move it directly to this 5 volt, the integral of moving this charge along this straight line, just going directly up from 10 to 5, would be 5 minus 10. Okay, if I took the charge and instead went all over the place and ended up here, it would still be 5 minus 10. This is what it means by being independent of path, dependent only on the potential at the endpoints. And that is a feature of a conservative field.